In this video, we'll be looking at the Friedel-Crafts acylation reaction. This is something that you're going to have to use a lot in organic chemistry, and so it's important that we understand what's happening. It's not so often that you'll have to be using the mechanism, though it is, I guess, important to understand why this works and how this works. But more so, what you need to know for the future when you're doing a lot of synthesis problems is you need to know the different reagents that are involved in this reaction and what these, the starting material is and the product. So, like we were looking at with nitration, sulfonation, and these other reactions, we're going to be starting off with a benzene. So we have our benzene here, the six-membered ring, and we add in our double bonds. And so what's going to happen here in the case of the Friedel-Crafts acylation reaction is we're going to first react this benzene with some sort of acid chloride. So we have our chlorine here, and so what we can keep in mind is that this acid chloride can be as long as we want to make it. We can make this a much longer chain like so, but for demonstration, let's just leave it as this. And this is also going to require a Lewis acid catalyst. So a Lewis catalyst such as AlCl₃ is going to also be necessary for this reaction. So let's make this arrow a bit longer. And the second step is we're going to have to quench this. We're going to have to react this with water. So it's important that you number these two steps. You don't want to lose points for not doing so, because it is important to distinguish the fact that these reactions are two separate steps. Firstly, we're reacting with the acid chloride in our AlCl₃, and second, we're going to react with the water. These are not occurring concurrently. And so at the end of this reaction, what you'll see is you'll end up with just our benzene as usual. But we'll also have now this group attached to it. So this is the acylation reaction. So what you'll notice is all we're doing really is if we're taking our acid chloride and we're replacing this chlorine with our benzene here. So that's the only difference. That's the thing that we're doing. So if we wanted to add this sort of group to a benzene, one way to do it would be through our Friedel-Crafts acylation. So again, if I had we had our benzene here reacting with a even longer chain, for instance, like this, in our AlCl₃. Oh, sorry, number 1, and then secondly, water. Remember to number these steps on your arrow as well. You're going to simply end up with our benzene. Now, instead of having this chlorine, we're going to have, how many do I have? 1, 2, 3, 4. That's 1, 2, 3, 4. Something like this. So clearly this is a very useful tool. So now before we get into the mechanism, you'll notice that this mechanism is going to be very similar in some ways to things we've already encountered. And that's because this Friedel-Crafts acylation reaction is another type of electrophilic aromatic substitution. Another one of those EAS reactions, which we've already encountered previously. So starting off, what we'll see is we're going to react the acid chloride. We'll react our acid chloride with our catalyst. So that is with our AlCl₃. So what we'll see is the electrons in the lone pairs of our chlorine are going to go and attack our aluminum. This is going to result in a complex that looks something like this. We're going to have our acid chloride now bonded to our AlCl₃. And what's important to know here, right, is that we have our aluminum having a charge of -1 and our chlorine as a positive charge here. And so what we can see then is this results in our chlorine sort of breaking off here, and we end up breaking this bond as we push off with these electrons towards the positive charge that we have on our chlorine here. And this is going to then give us our AlCl₄, right, because this chlorine is now part of this AlCl₃, so now we have AlCl₄, and what we'll also end up having is an ion here, and this is known as the Acylium ion. So we're going to simply draw what we had here before, something like this, right? Except now we have a positive here in place of where our chlorine was initially bonded. So we have this ion, this Acylium ion, which we can also right? This Acylium ion can also be just drawn out. These three lines just mean it's equivalent to us just drawing CH3 bonded to a C, double bonded to an O, and our carbon here is the one that has the positive charge. So this is just another way of drawing out acylium ion. So now, this is what we're going to react with our benzene. So, kind of keeping this here as reference, if we now draw out our benzene molecule here, we can see this is again going to be very similar to what we've seen with other EAS reactions. We can draw out our two hydrogens here for clarity. So we have our two hydrogens here, and now we have this acylium ion. So this is our methyl bonded to a carbon that has a positive charge, double bonded to our oxygen here. So what we'll see is the electrons forming this double bond will go on and attack the positively charged carbon. Once this happens, we form a complex here where we have our benzene. Here, I think I could actually move these out of the way now. So we'll have our benzene here. These two double bonds are still present, but we can see that the double bond, or the electrons that form this double bond, were now used to form a bond with this carbon. So now this double bond no longer is existing, and in its place we can see we have the initial hydrogen from before, but now we also have this carbon which is double bonded to an oxygen bonded, which is also single bonded to our methyl group here, right? And we still have the remaining hydrogen here. However, we saw before that this carbon was a part of a double bond, which no longer exists. The carbon above here is sort of satiated in that it has now this acylium bonded in place, so there are some electrons in place here, so this carbon is doing all right. But the carbon, beneath it has not been replaced with anything, and so we have to have a positive charge here. We can draw it in here. So this positive charge is important to include. So this is a carbocation. So while we have this carbocation, what we can do instead is we can use the electrons that form the bond between this carbon and this hydrogen. We can push those downwards here. We can push those down, and what that ends up doing here is something like this. We end up forming something like this. Now, while I was doing this, I intentionally left out one small step, hoping that you caught it, based on what we've learned from our other EAS reactions. Can we simply, and it has to do with this step here, are we able to simply push these electrons from the hydrogen onto the carbocation? Well, no. We need a base to attack that hydrogen, which then ends up pushing off the electrons towards the carbocation to form this double bond. So the thing that was missing here is that we need to include a base. So we have some base here, right? With its electrons is going to attack our hydrogen, which then breaks the electrons or allows the electrons in this bond to collapse onto the positively charged carbon, forming this product here. Now, what's important to keep in mind also has to do with the reason that we have to react this with water. So we now have formed this product that looks something like this, right? We can just draw this circle to delineate the double bonds in our benzene, but what we notice is now we have our product here. So what happens now is the fact that this reaction is not occurring with solely one AlCl₃, right? It's occurring in a solution where there are multiple aluminum chloride molecules. So what's going to happen then is another AlCl₃ is going to want to go and form a complex with this oxygen. So what will end up happening here is we'll get some complex molecule that looks something like this. But now, once again, we have to keep our charges in mind. So this is a negative, this is a positive. So a complex like this is going to readily form in this solution from our initial product, which is why it is important that we follow through with the second step, which is reacting with water. When we react with water, we're able to break off this AlCl3. We're able to get rid of this AlCl3, giving us our desired product, which would look something like this. Again, this is just the line notation for the same thing that we're looking at over here. But again, that's why it's important we react with water. We quench here with water because we often have our acid catalyst here, our AlCl3 in this case, going on to form a complex with our oxygen, which is not what we want. So we need to react with water in order to break this off. Hopefully this is making sense. So that brings us to the end of this mechanism. But there is one other thing that I was, I wanted to do in another video, but I might as well include here. Is basically, say we want to create a molecule where we have our benzene, and it looks something like this. How would we do this? Well, we know how to create something that would look a little more like this, right? We're using our Friedel acylation that we just learned. We know how to create this molecule. How would we do that? Well, we would react a benzene, right, with an acid chloride, right? With AlCl3, and step 2, water. So in that way we can create this. But then how do we go from here to here? We need to get rid of this water, this oxygen here. Here we formed a ketone. We're able to successfully form a ketone using our acylation reaction. Well, now how do we get rid of this oxygen here? So in order to get to this desired product, what we need to do is called reduction. We need to reduce this ketone. So without getting into the details of the mechanisms, there are two ways that we can reduce our ketone here to form our desired product. So one of those is going to be called the Clemmensen reduction. Clemmensen reduction. And the second one is called Wolff-Kishner reduction. Wolff-Kishner reduction. So these are both reduction mechanisms that you'll be using again a lot in a lot of different synthesis problems. And so it's important that you're familiar with the different reagents and the reaction conditions under which we can do each of these different reduction reactions. So there's two ways, like I said, to do this. If you want to start off with our Clemmensen reduction, what that's going to look like is something like this. So if we wanted to, I'll draw it out here. If we wanted to start off with our benzene, or let's not start with the benzene, let's start with the acylated product here. Let's say we have this product here, which now, if we want to reduce this ketone, what we're going to want to do is react to zinc in. So we're going to be reacting with zinc over mercury, like this, and this is going to be in HCl and ethanol, which we can abbreviate like this. When we write ETOH in this way, that's the same thing as ethanol. So if we do this reaction, we're going to be able to reduce our ketone to form our desired product here. Now there's another way that we mentioned, which is going to be, well, this is our Clemmensen reduction. So the other way is going to be using our Wolff-Kishner reduction mechanism. So once again, we can start off with our benzene here. Benzene, which is acylated. And here, if we want to do the Wolff-Kishner reduction mechanism, we're going to need a couple more reagents. Oops. And now what we're going to also need is something that looks like this, as well as our KOH. And all of this needs to be occurring at 200 degrees Celsius. So there's a lot more details going on here for our Wolff-Kishner reduction. But these are all necessary, and what will end up happening is the same exact thing that we get from our Clemmensen. Obviously, a completely different mechanism, but the desired product will be the same. We'll be able to effectively reduce our ketone here. to form our desired product. So anyway, that brings us to the end of this video. I was expecting to include reduction in there, but here we go. So hopefully everything made sense. If you have any questions, be sure to leave them in the comments below. If this video was helpful, please show your support by liking and subscribing, and I will see you in the next one.